Hello, everyone, and welcome to the Apalachicola-Chattahoochee-Flint River Basin Drought and Water webinar for the month of January. Welcome to our first webinar of the year 2021. My name is Rachel McGuire, and I am with the Auburn University Water Resources Center located in Auburn, Alabama. If you're new to the webinar, I have a few housekeeping items to address. We will have time at the end of the webinar for comments, questions, or any points of discussion after all our speakers have already gone. During the webinar, feel free to use the question box on the GoToMeeting tool panel. You can type your questions, or at the end of the webinar, you can also use the raise your hand function by pushing the hand icon on that same tool panel. Our speakers today will be David Zierden, the Florida State climatologist at the Florida Climate Center housed at Florida State University. He'll speak with us about our current drought status, as well as our seasonal forecasts and outlooks. We have Tom Littlepage, the branch chief of the Alabama Office of Water Resources with State of Alabama input. We have Paul Inkhorn of the USGS South Atlantic Water Science Center speaking to us about our streamflow and groundwater conditions in the ACF. We also have Troy Ephraim of the U.S. Army Corps of Engineers Mobile District to update us on our current ACF reservoir conditions. We have Jeff Dober of the National Weather Service Southeast River Forecast Center speaking with us about our streamflow forecast for the region. And we have a special presentation today by Dr. Hamid Moradkhani of the University of Alabama, where he is the director for the Center of Complex Hydrosystems Research. As a reminder, speakers, let me know when you need a cue for your next slide. And with that, I will start with our first speaker, David Zierden. Ready when you are.
Okay, yeah, thank you, Rachel. Can you hear me?
Yes, I can.
Okay, we'll go ahead and begin then, and we'll start like we often do with weather that's in the news. And in the news today is the severe weather and very potent tornado that hit in just north of Birmingham in the overnight hours. Over on the left, it shows a picture of the damage. There was one confirmed death and at least over 30 injuries from this potent tornado. It also drove home a couple key messages, and one is that these kind of strong tornadoes can occur even when the environment is only in a marginal risk for severe weather. So even if it's only a marginal risk by the Storm Prediction Center, always have your weather radio or other alert system ready in times of unsettled weather. The other lesson is that there is a connection with the Pacific Ocean, specifically the La Nina phase. A study done years ago here at COAPS and other studies confirming this since then show that during the La Nina phase, tornado frequency is actually enhanced across the deep south and the southeast, what's known as Dixie Alley. And this enhanced tornado activity occurs basically from January or February through the spring tornado season. So we've got the Pacific Ocean enhancing the risk, and also so we can probably look forward to more bouts of severe weather as we progress through the winter and spring season. On the next slide, and before we get too far into the drought topics, I want to do a quick review of the climate of 2020, calendar year 2020. Here I show the statewide ranking of temperature in the calendar year of 2020 since 1895, or 126 years of data. And some things that stick out, every state in the union was warmer than normal in 2020. All the states in that darker orange were in the top 10 warmest years on record. However, there was no state that had the warmest year on record, but there were 10 states with the second warmest year on record, including Florida and many states in the Northeast. For Florida, through the month of November, we were far out in the lead for having the warmest year on record. But on the next slide, you'll see in December, we actually had, I'm sorry, I skipped ahead, but December was actually colder than normal and brought us back down to second place. On this slide, we show the similar graphic. It shows the precipitation rankings since 1895. And we see a lot of darker green across the Southeast, including Alabama and Georgia and the ACF Basin. All these states ranked as one of the 10 wettest years on record. And we also see the difference between the wet eastern United States and the very dry western US, where Nevada and Utah experienced their driest calendar year on record. So on the next slide, we'll talk a little bit about the cold December we experienced here in Florida and the Southeast, in particular the ACF Basin. The map on the top left shows the departures from normal for temperature in the month of December, and very warm temperatures across the upper Great Plains, the Dakotas, where it's 7 to 10 degrees warmer than normal. But there in the middle and lower ACF and the peninsula of Florida, we see 1 to 3 degrees actually below normal. And this kind of goes against our typical La Nina thinking, where it usually brings warmer and drier weather. But partly to blame is the Arctic Oscillation and a weaker and more unsettled polar vortex, basically since the first week of December. At the bottom graph, you see that this Arctic Oscillation has been negative since the first week of December. And with that more variable polar jet stream and polar vortex, it's led to cooler weather here in the Southeast and the potential for more winter storms along the East Coast. And I'm sorry, I had to sneak Bernie Sanders all bundled up in there somewhere. So you got your Bernie Sanders meme for today. So on the next slide, we'll talk about since December, January temperatures across the Southeast have returned back to warmer than normal, which is kind of the new normal now. And we see that across Florida, Georgia, Alabama, temperatures were running anywhere from 1 to 3 degrees above normal so far in the month of January. So on the next slide, we'll start taking a look at the drought situation. And this is the current US Drought Monitor, where we have no areas of real drought or D1, but we have several areas of abnormally dry across west central Alabama, west Georgia, the Big Bend of Florida, and the Georgia Atlantic coast. And these areas are starting to pop up more frequently and expand in size as we go through the winter. So on the next slide, we'll start taking a look at recent precipitation. Oh, we can skip this one. I think that's an artifact from last month. We'll begin by looking at the University of Alabama Huntsville's Lawn and Garden Moisture Index, which across the ACF Basin, Georgia and Alabama, still shows normal to even moist conditions, a little bit of dryness in the headwaters region around Atlanta and Lake Lanier, but mostly around near normal through the ACF Basin. We are starting to see the peninsula of Florida dry out in response to very little rainfall over the last 30 days or more. And just to caution though, this Lawn and Garden Moisture Index, the amount of effective rainfall it looks for in the wintertime is much less than during the summer. So this index is a lot slower to dry out in the winter months when evapotranspiration is much reduced than it is during the summer months. So on the next slide, we'll start looking at recent rainfall. And these are radar estimates of rainfall over the last 7 days. And you see most of the ACF Basin, Alabama, Western Georgia, all in the green colors, which corresponds to anywhere from 1 to 2 inches, maybe a little more of rainfall in some areas, but pretty widespread, 1 to 2 inches or more. However, this is still a little below climatology, which is 3 to 5 inches of rainfall per month. So we are starting to accumulate deficits. And we'll see that on the next slide. This was rainfall over the last 30 days. And here we see heavy amounts in the Florida Panhandle and in the lower ACF from a system a couple weeks ago where we had a stalled frontal system. But elsewhere in Alabama and Georgia, amounts were much less, only 1 to 3 inches, like I mentioned earlier, which is below the climatological normal. And also you see very little rainfall, only fractions of an inch over the peninsula of Florida. On the next slide, we'll take a look back at the last 90 days, and now this is departures from normal, not actual amounts. And here you really see the drying trend where all of Alabama and western Georgia are mostly several inches below normal now. You can still see the impact of that stalled frontal system in South Georgia and the Florida Panhandle, but you also see the drying that's occurring in the Florida Peninsula. The moisture areas down in South Florida are actually an artifact from nearly 3 months ago when they got some fall rainfall. So with that, we'll start looking ahead. And this is the 7-day quantitative precipitation forecast for the next week. And highlights of this is very heavy precipitation amounts forecast for California and the West Coast, with a series of potent storm systems forecast to come ashore this week. However, over here in the Southeast, you do see the forecast for amounts of an inch or more across the ACF basin, and that's mainly due to this current system that's pushing through today and tomorrow. But after that, it looks like we will have a drying trend for the remainder of the week. On the next slide, we'll start looking at the Pacific Ocean and our seasonal forecast. And here's a map of current sea surface temperature anomalies showing still a very strong La Nina pattern with very cold, colder than normal ocean temperatures in the central Pacific along the equator. We do see that the eastern Pacific is more of a mixed bag and is starting to warm a little. However, looking at our Nino 3.4 index on the bottom, it's still well in the La Nina range, running about -1.2 this week, which is below this threshold for a strong La Nina, but still in the moderate to strong range. So we're still well in the grips of the La Nina phase in the Pacific Ocean. And on our next slide, we'll see is how long that's forecast to remain. Like the previous few webinars, there's a 100% chance that we'll remain in this La Nina phase through the winter time, December, January, and February. As we get into March, February, March, April, the probability of remaining in La Nina starts to drop, whereas when we get into the real spring season, March, April, May, it's only a 55% chance that we will still be in these La Nina conditions. And over on the right just shows the model spread of the different forecast models for the sea surface temperatures in this Nino 3.4 region. As I've preached many times before, this is a very difficult time to forecast the phase of the Pacific Ocean when looking through the spring at the coming summer and next fall. And the large spread in the different models really convey this. And we even have a couple real outliers showing drastic cooling and another one showing fairly drastic warming in the next few months. But I think we can disregard those. So on the next slide, with this in mind, I know Tom Littlepage has been hammering this home that the real risk for developing drought comes not necessarily during the fall and winter of the La Nina phase, but as we get into the warming temperatures in the spring. So over on the left, I updated this composite, and it's a composite of rainfall anomalies for the February, March, April 3-month period. and where I grouped together all the past La Ninas of similar strength. And you see a well-defined pattern of very dry along the northern Gulf Coast and in the lower and middle ACF basin, the Florida Peninsula, very dry conditions anticipated in the next 3 months based on this La Nina composite. And you can also see the storm track of enhanced rainfall up the Mississippi and Ohio River valleys. So keep that picture in mind as we go to the next slide. This is the official seasonal forecast from NOAA's Climate Prediction Center. And over on the right is the rainfall forecast for the February, March, April time period. And you see it's basically the exact same pattern as that composite of past La Ninas that I showed you on the previous slide. And that same region of enhanced rainfall up the Mississippi and Ohio River valleys. And over on the left is the temperature forecast for the next 3 months, where with the exception of the Pacific Northwest, most of the country is forecast to be leaning towards above normal temperatures. So with these forecasts in mind and the continuation of La Nina conditions, on the next slide, we'll see the seasonal drought outlook, where we see that drought is forecast as drought development is likely across the lower and middle ACF basin and the same areas of Georgia, Alabama, and Florida where we're starting to see that D0 or abnormal dryness pop up. So with that, we can look forward to expanding areas of abnormal dryness or possibly even the development of moderate drought in the coming months. And with that, I think I'll wrap it up with my summary points. 2020 was a very warm and wet for most of the Southeast United States. However, December of 2020 was the first colder than normal month in the state of Florida for nearly 3 years. In January, we have returned to slightly warmer than normal temperatures over the last 30 or so days. Looking at drought, there are small pockets of abnormally dry over North Florida, Georgia, and Alabama. However, rainfall deficits are starting to build across most of the ACF at time periods of 30 to 90 days. We're still in a La Nina advisory, according to NOAA, with 100% chance of it continuing through the winter season and a 55% chance of it continuing through the spring and into early summer. And based on this, the CPC seasonal forecast favors above normal temperatures and below normal rainfall, especially in the peninsula of Florida. We have had this negative Arctic or North Atlantic oscillation kind of overwhelm the typical La Nina impacts thus far this winter, but things look like the pattern is shifting towards a more typical La Nina type winter. And this is the point I really want to hammer home, is that drought development is a risk in spring as La Nina plays out, especially in the lower ACF basin. And you know, the whole NIDIS program is an early warning system. So consider this an early warning that we really have to be monitor closely drought conditions as we go through the spring and be prepared to take action.
Thank you, David. Now I'll turn it over to Tom Littlepage with the state of Alabama input. When you're ready, Tom.
Go ahead. Show the first one. So this is the slide from last week, which showed a substantial increase. I think this was 23% versus 5% for the previous week. And I think I was overly optimistic. I submitted this, I think, on Friday, and we were hopeful that some of the rainfall that was forecasted would be relatively widespread. It turned out at this point not to be so, such that the map that will come out this week, I think, will show basically the same, with the potential to add a couple of small D1 spots to the state. So I think it just reinforces that we're in this mode of hit and miss some of the rainfall. We don't have significant drought conditions, but we are watching it. Next slide. We have not revised our state level drought declaration at this point. So we continue to, from a declaration standpoint, not to have a clear map and not have a expressed declaration level for any part of the state. But we are continuing to monitor conditions. As David alluded to, the La Nina event is still strong, and we anticipate that it will intensify its signal as we get into the southern part of the state. And so we'll watch that carefully. Next slide. And if you, as I've talked about, we continue to publish information. One of the things I'll point out on here is our GIS portal that you see here, the third bullet down. We are updating that weekly, and if you want to see drought or flow conditions for both regulated and unregulated spots, I think around 72 spots around the state, you can refer to that. And then next slide. So I had hoped that we should see a reduction. I don't think it'll work out that way, but we are continuing to monitor. I think the important thing is that there has been no significant impacts from ag or public water systems that have been reported to us. So it's something we are continuing to monitor, but the good news is at this point, we're not seeing any of the impacts based on these relatively moderate drought conditions. The last slide. It may be that if we are starting to see D1 and some increased dryness, that over the next few maps, we'll see that we may determine that it's time to schedule a meeting of our technical advisory group known as the MIG. But at this point, there are no meetings scheduled. And that's a short and brief update from Alabama's perspective.
Thanks, Tom. Now I'm going to turn it over to Paul Inkhorn with our Streamflows and Groundwater Conditions when you're ready, Paul.
Yeah, good afternoon, everybody. So move to the next slide, and we'll start as we usually do here, looking at our current stream flow conditions across the southeast. And the image on the right was pulled this morning. I waited hopefully to get some flows to show more flow. You know, some of the gauges at 7 this morning were still showing some lower than normal flows, but across the whole basin as a whole, flows are still in the normal range. With some exceptions, some low flows due to regulation, and what we're seeing in at least around the metro area is some high flows and above the normal type. And obviously that was from the rain that came through early this morning. So we'll take a look at the next slide. And this is new. I put this in to try to give an idea of what's happened the past 45 days here. So the graph on the left is a bar graph, and it shows the percentage of stream gauges in each of the flow percentile classes. So looking at the last column there in the graph, and then on the table you see January 25th. So the flow classes rate from or rank from low to high flow. So we had 0% gauges in low or ranked as low flow. 3% were much below normal, and so on and so forth across, with 78% of the stations ranking in the normal flow range. So that's just an indication of the last 45 days, and these are the 75 sites that have the what we consider long-term data. So it's 30 years or more. And so, by way of comparison, looking at December 25th, Christmas Day, we had around 44% of gauges that were ranked in the above normal, and it looks to be around 4% in the much below normal. So you can see how things have started to dry out a little bit as flows have reduced. And these are gauges in Georgia, so this is not just ACF, this is the whole Georgia proper. So hope that makes sense. Anyway, we'll move on to the next slide. And this is a graphic we're used to here. So this is the below normal 7-day average stream flow. And again, this is showing Some of the reduction in flows last month, there was really no below normal flows in the ACF, but the past month we've seen some lower flows, and you can see there in the bottom graph that majority or most of Alabama, for instance, is showing to be moderately in hydrologic drought or below normal. And then there is a portion of the upper Flint that is showing to be ranking in the below normal percentile. So we are seeing some drying out, and that's a result of the last the last month or so, as David had pointed out. So we'll go to the next slide and we'll start looking at some of our, these are 28-day averaged stream flows, and they are compared to historic rankings for the daily mean. So these two stations here are Lake Lanier inflow. You can see that the solid black line is the averaged, so it's a moving average 28 days. So both of those stations have just crossed from above normal to the normal range. So we're looking good, but we'll have comparison. If you look at January of 2020, you'll see we were pretty much in the same boat there as what we're seeing right now. But then, of course, February and March, we had some pretty significant flow precip events that, as in the case of Cornelia, created a new record 28-day average flow. So we're kind of, we're in the same boat as we were, so to speak, as last year, and we'll see what rains come in the springtime. And as David pointed out, that may be a little bit less expected than what we would hope for. So anyway, we'll move on again to the next slide. And so now we're moving just downstream. This is Chattahoochee, Atlanta, and Whitesburg. And Atlanta right now is right at the, I'd say the 80th percentile with above normal average 28-day flow. And Whitesburg is right at the 75th percentile, trending towards normal. All right, next slide, please. We'll move again further downstream. So this is West Point and Columbus. Both 28-day average flows today are in the normal range. And then the next slide, we'll swap over to move over to the Flint River Basin. So Griffin and Carsonville, again, are right there in the normal, as to be expected. But comparing that, to what we saw this time last year, flows were in the above normal, right around 1,000 and 10,000 CFS for the 28-day average flows. So although we're still in normal, we're significantly less than what we were seeing this time last year. All right, next slide. We'll move further downstream to Albany and Bainbridge. And again, both these stations have 28-day average flow ranking in normal conditions. And then next slide. This is Apalachicola River at Chattahoochee, and that is also showing flow to be in the normal range. So, and next slide, we'll transition to groundwater conditions. This is our real-time network in the state of Georgia. So our current conditions are on the right, and as usual, it's a mixed bag across the ACF basin. The very northern point there, the orange point, which is ranking at below normal, that's right at the headwaters of the Chattahoochee. That's actually Unicoi State Park. And so as you move down through the basin, we're having the majority of the sites ranking in normal, with some above normal conditions around the Albany area. And if you'll notice, compared to the previous brief, we've brought 3 or 4 more stations online. So we're continuing to instrument those well sites to be real time, so we can get a more real-time picture. So we'll move on to the next slide. And these are just our 2 reference sites here. So Miller County, graphic on the left is our previous 7-10 days. and showing a slight decrease in well elevation there. But if you look on the right, I mean, relatively speaking, we're just coming off a period of above normal elevation there. So we've just crossed into normal conditions for Miller County. And the next slide is Doherty County. So same thing there. We just saw for the month of January, well elevation move into above normal, but we're trending back now into normal for this time of year. And so the last slide here, we'll just wrap up with a quick summary. So real-time stream flow ACF basin currently in the high to much below normal range, mixed bag there. The upper Flint River Basin is currently ranking as moderate hydrologic drought for the 7-day average stream flow, 28-day average stream flow for the Chattahoochee, currently ranked from above normal to normal. And Flint River currently ranking in the normal range. And then the last point was real-time groundwater levels for the basin range from above normal to low. And that concludes it, Rachel. Thank you.
Thanks, Paul. Now I want to turn it over to Troy Ephraim with our reservoir conditions. When you're ready, Troy.
Hey, can you hear me, Rachel?
Yes, I can.
Great. So we'll start with Lake Lanier. The current pool elevation was 1070.05. And over the next 5 weeks, we're predicting that we'll be right at guide curve of 1070. Next slide. We'll move down to West Point. The current pool elevation 628.47. And right now we're just kind of following the median as we get ready to approach the navigation season, as well as fish spawning coming up in March. Next slide. We'll move down to Waltrip, George. The current pool elevation 188.39. And that's the same, we had the storm band move through, and so we'll be seeing some effects of that, which is why over the next couple of weeks we'll see an increase in the pool elevation that will get back closer to guide curve. Lastly, we'll move down to Lake Seminole and Jim Woodruff Dam. See pool elevation 77.49, and we are expecting to be around 77.2 over the next 5 weeks as we're getting ready to handle fish spawn as well as navigation. Next slide is the ACF Basin Composite Conservation and Flood Storage. Right now we're in Zone 1, and with all of our projects full, we're projecting to remain in Zone 1 over the next 5 weeks. So in summary, the inflows into the project, as was just mentioned previously, have been normal to slightly above normal, and currently the projects are operating right at or just above winter pool guide curve elevations. And for the ACF system conservation storage, we're currently in Zone 1, and we're forecasted to remain there over the next 5 weeks.
Thank you, Troy. Now I'll turn it over to Jeff Dober with our Streamflow forecast for the ACF. When you're ready, Jeff.
Okay, thank you, Rachel. Well, I thought I'd begin by showing our meteorological model-based ensemble river forecast. I showed these last time. This time I put each one separately in a slide so everybody could see the discharge values as well as the forecast. And so again, what this is a 10-day forecast, and it uses the meteorological models rainfall forecasts over those 10 days to drive our hydrologic model to provide you guys with some insight into what kind of flows that we're going to potentially see at these certain locations. And I picked a few. To begin here, this is Lake Lanier. These are the inflows into Lake Lanier. And so the big thing is right now we're not expecting any significant flow events, at least over the next 10 days. But we are expecting several, two to three, as you can see, smaller events. Now on the chart here, the black line is sort of would be the median of the ensemble forecast, and the orange that's the more likely range. That's the most likely range for the inflow forecast. And then we have the outlier range, and that's the blue lines there. So to get a feel for the highest confidence, that's that orange range as we go out through the next 10 days. So these are the inflows. Again, nothing significant at the top of the ACF. If we go on to the next slide. Now here we're in the middle Chattahoochee here at Whitesburg. Again, not expecting any significant events, no significant flows, staying well below flood stage over the next 10 days. And I'm jumping down the river here. If you want to see more points, potential points, Rachel, I think, has the web address where you can get these forecasts online as well. So we'll go down to the next point here. And now we're jumping over to the Flint River at Lovejoy. And again, you can see that we've got an event here. We just got over one event yesterday, and we're going to see another stream flow event as water makes its way down sometime on the 28th, 29th. And again, another one out there on the 2nd. And just looking at today's forecast, because these are the ones that were run yesterday that I provided for slides, looks like we're going to have something around the 4th or 5th of February as well. So 2 to 3 events over the next roughly 10 days to give you guys a feel for it. Let's go to the next slide here. We go all the way down to the Apalachicola, the bottom of the ACF. And you can see for the most part, we're more or less routing through the system now. And again, no significant events, stream flows relatively down around that 17,000 flow range, which is pretty good for this time of year. No flooding, and so far, pretty decent in the normal range type flows. So where's this lead us to? The next slide. Here's our 1 month forecast. And again, I talked about, looks like mostly normal right now in the next 10 days. And it looks like that trend will continue over the next month, leading us out through the end of February. And again, this is based on the current reservoir levels that Troy just talked about, and then the current stream flow trends that Paul was talking about, as well as the medium range meteorological models and the CPC forecast that David had pointed out. So right now, mostly near normal, with the exception of we may see the potential, just because we're in that sort of equal chance at above or below or near normal rainfall, that we're sticking with the trends, which has been above normal for lake linear inflows. So near normal in the 1 month. As far as the 3 month, again, these are all based on the current trends and the CPC forecast, but notice our pie charts, how they're indicating higher chances at near normal or below normal, higher chances relative to our December forecasts. So this falls in line sort of what David was saying, sort of a trend toward drier weather. But on average, I think we're going to, through at least April, this would be February, March, April, our forecast, we're going to probably be in that near normal range is our best forecast guess. And keep in mind that water resources and stream flows, they'll lag the drier weather. So if we do get into drier weather, and for March, drier than normal weather for March, that'll lag into the late spring and early summer as far as water resources. Also keep in mind that February, March, and April, these are our key water recharge period months, our primary recharge period for the ACF. And that is the period of time when flows are at their highest. So, and these, sort of Paul pointed this out, this is evident on his stream flow charts that he was showing. But also keep that in mind that that we are going into our stream flows that may be in the above normal range for November and December could potentially be in the normal range if we stayed at those same stream flow ranges. They could potentially be normal stream flows during February, March. So again, overall, in our summary here, we're not anticipating any flooding in the short term in the ACF. Our 1-month Streamflow forecast is calling for near normal with potentially above normal flows on the far upper Chattahoochee as far as the inflows in the Lake Lanier. Then our 3-month Streamflow forecast, again, continued near normal. And again, as I reiterated, these 10-day forecasts, if you're interested in more than the forecast that we've shown, these are our guidance forecasts. You can go to that website. But for our official forecast, you could go to that official river stage and flow forecast website that I have right there as well. And that's all I had, Rachel.
Thank you, Jeff. And now we have a special presentation from Dr. Hamid Moradkhani of the University of Alabama, where he resides in the College of Engineering and is director of the Center for Complex Hydrosystems Research. So I am ready to go when you are, Hamid.
I am. You hear me well, Rachel?
I do.
Great. Good afternoon, everyone, and thank you for the invitation and opportunity to present some of our work on drought monitoring and forecasting, and specifically recent development related to the ACF region. Next slide, please. Well, I'd like to start my presentation by giving you a bit of a background on some of the research we've been conducting in the past decade related to drought, and acknowledging the first authors who were my PhD students or postdocs over the years. On the top left, you see a paper we published as part of the special collection in the Advancing Drought Monitoring and Forecasting in Journal of Hydrometeorology in 2013. That was organized by Drought Task Force, and given that it received a significant attention in the community, we further extended the study through a special temporal drought forecasting within Basin framework that you see on top right. And then through another funding from NOAA program, we developed the drought monitoring system using remotely sensed soil moisture assimilation, and used a sophisticated data assimilation framework called particle filtering. And that was applied over the Pacific Northwest in Columbia River Basin. Then we extended the work to drought forecasting by combining this framework using data assimilation for drought monitoring with the framework that you see on the top left for forecasting at seasonal scale. And we developed a combined dynamical and a statistical approach. Again, the application was over the Pacific Northwest. Then we extended the product over the continental US, and we wrote a book chapter based on the invitation we received from the AGU monograph on global drought. And that's the last one you see at the bottom of this slide, the probabilistic framework for agricultural drought forecasting. Next slide, please. And here I just wanted to mention that we've done quite a bit of other works related to drought. For example, sensitivity of drought recovery forecast to land surface initial condition, and a book chapter we wrote related to drought, remote sensing of drought, and looked at the vegetation health index, soil moisture, and again data assimilation, published in remote sensing of hydrologic extreme book. And we also looked at the hydrologic drought propagation and recovery, considering both water quality and quantity. And that was studied first over California, and then we extended the work over the continental US, again, looking at both water quantity and quality. In parallel to that, we've been conducting drought vulnerability studies, and through international funding, we did socioeconomic vulnerability analysis, a multidimensional framework over Africa, and North Africa and MENA region, and then drought risk study that I'm not showing here. That motivated us to look into the drought vulnerability in the United States through an integrated assessment that we published recently a few months ago. And this was this went to social media and NOAA website, etc., and some other website, looking into drought vulnerability, actually relative drought vulnerability across the continental US. Next slide, please. And going back to drought monitoring and forecasting and statistical dynamical framework that I mentioned, we wrote the book chapter related to that. Actually, we developed that book chapter, I should note that, 2 years ago, but the review process has been slow for this book, especially given the pandemic. This last year, everything was very slow, and just last week I received the proofread of this book chapter. I'm expecting to appear maybe in a month or so. In this framework, I should mention that we just focus on soil moisture as the main driver of agricultural drought. And in that framework, we use the meteorological forcing from NLDAS hydrologic model using variable infiltration capacity. Then we assimilated the land surface soil moisture data using satellite data into using an ensemble data assimilation scheme. Up to this point, we have a drought monitoring product. And then we combine that framework with a probabilistic cupola model that we published years ago in 2013, the first slide that I showed. And we developed the drought forecast at seasonal scale. Next slide, please. And in this slide, you see that multivariate statistical approach for drought forecasting. In this colorful map on top left, you see a probabilistic map showing that how we can know the probability of drought in a spring on the y-axis given the drought condition or streamflow condition or water supply on the x-axis in winter. So for example, if we experience any drought, for example, drought category D1, and what is the probability of experiencing again D1 or D0 or D2? So this graph shows that probability, and if you are in red zone, we have higher probability that can be directly characterized here. And the two-dimensional of that figure is on the lower left that can be seen in our papers as well. If you go to next slide, please. And here I'm showing a deterministic forecast and probabilistic forecast, left and right for different lead time. Short term is 1 month, and medium term 2 months, and long term 3 months forecast. Deterministic forecast, it just tells us if you're expecting any drought and within any category. And on the probabilistic one, we can actually specifically say, okay, at any grid cell at 1/8 of a degree resolution, what is the probability of experiencing any drought? Not only drought, but also what drought category, D1, D0, D4, etc. And next slide, please. And now let's talk about the very recent enhancement we've been conducting, the sequence of drought occurrence and impacts, and why we need to assess drought using an integrated approach. Well, you know that drought is part of the natural climate variability and therefore can be observed in all climate regimes. Unlike aridity, drought is a temporarily abnormal phenomenon, usually characterized by lower than average water availability for the population or for the environment. So different types of drought occur at different time scales and are intimately interrelated with each other. Therefore, an effective drought monitoring system should integrate multiple drivers, types, and characteristics of droughts for better adaptation and mitigation. So these were the motivation for us to develop a continental drought monitoring using satellite soil moisture data assimilation while designing an integrated drought index that can holistically account for different drivers of drought like precipitation and evapotranspiration. The framework is shown on the lower right, but I'm not going to go over that technical sophistication here. Next slide, please. And drought monitoring using our integrated approach. Here I'm showing some comparison of our product with other agencies' drought reports like NOAA, CPC, and NCDC and NASA GRACE. Here are the 4 examples. Our product is shown on the right for different months in year 2017. For example, the mild drought occurred in some areas of the southeastern continental US in mid-spring in April, panel 1, similar to the NOAA Climate Prediction Center product on the far left of the slide. And the second panel, during late summer in July 2017, severe to extreme drought prevail in northwestern corners. Specifically in Montana, consistent with the result from USDA topsoil moisture observation and NOAA NCDC, as you see on panel 2 on the left. And in early fall, in September, severe drought occurred in the southern Illinois, West Virginia, Kansas, and northwestern areas, consistent with the precipitation anomaly shown by the SPI from NOAA report. And in late fall, severe to extreme drought happened in central and southwestern areas, especially in Arizona, corresponding well with the gravity recovery and climate experiment GRACE-based actually root zone soil moisture index. So what I'm trying to say here is that our drought maps are not only consistent with the USDM maps, they are in good agreement with some other products like CPC, NCDC, and NASA GRACE. Next slide, please. And here I'm showing the benefit of our integrated drought index as compared to other drought indices. On the right, you see on top row, you see the USDM map for April 2015 and December 2016 and 17. And the second row is showing the standardized precipitation evapotranspiration index. The third row is showing a standardized soil moisture index, and open loop OL stands for open loop, meaning that it's just a simple hydrologic model run, of course, after the calibration. And the last row is showing the our framework standardized precipitation, evapotranspiration, and soil moisture index. It's a compound index to account for different drought drivers. We further investigated this here through multiple examples, and I'm showing just a couple of them here. On April 7, 2015, severe to extreme droughts were detected in large parts of the western US, in particular in California, by the USDM. And the SPSMI, our framework, better than other drought indices, such as SPI and model simulation or open loop, captures drought extent across the western US. Our drought map is also consistent with the NOAA report, and you can see both figures on the top left related to that, and the lower figure is about the NASA GRACE product, root zone soil moisture, and the consistency between these products. Next slide, please. And drought extent and spatial temporal correlation between the USDM maps and our integrated based drought maps. There are several temporal drought hotspots detected by the USDM, such as in October 2015, November 2016, and February 2018. The temporal drought hotspots detected by our index agree well with that of the USDM. And some of the differences also exist in the detected drought area between the USDM and this index. For example, this index estimates a smaller drought extent in January 2016 than that of the USDM. So this difference is likely due to several reasons, such as the inclusion of a streamflow or groundwater condition in the USDM that can be added to our framework as well. Next slide, please. And now enhancing drought monitoring system over the ACF region. In order to further enhance the performance of developed drought monitoring system, in addition to soil moisture, we can benefit from satellite ET observation within the drought monitoring system. And why ET? And well, ET is an integral part of the Earth ecological and climate systems. ET links the water, carbon, and energy cycles in the Earth system. Also, ET is the total amount of water required to grow a crop. It also plays a critical role in irrigation scheduling planning. And also during the onset of drought, or in particular flash drought as experienced in the Southeast, the soil moisture deficit is first experienced at the topsoil layer, and then through vegetation and evapotranspiration, the root zone soil moisture is further depleted, resulting in more pronounced drought. And finally, accurate estimation of ET and soil moisture facilitate detection of the human fingerprint on the water cycle and surface energy budget. And here is our framework for drought monitoring the ACF basin For soil moisture, we use soil moisture operational product system, or SMOPS, on the right that you see in the figure on the left, that combines soil moisture retrievals from 6 satellites, including GPM, SMAP, SMOS, and so forth. SMOPS spatial resolution is 0.25 and by 0.25 degree, and its temporal scale is 6 hourly and daily. However, we downscale this product to 1 kilometer resolution using our machine learning method that we developed a couple of years ago, and I will explain in the following slides. And for ET, we use the MODIS version 6 evapotranspiration latent heat flux product, which is an 8-day product produced at 500 meter pixel resolution. Next slide, please. And drought monitoring in the ACF basin, and on the left you see 4 columns. Open loop, which is the simple hydrologic model run using weak model, and evapotranspiration data assimilation only into this model. And the third one is the soil moisture data assimilation, and last one is the multivariate data assimilation. So in each row you see different performance measures like KGE, which is the Kling-Gupta performance measure, and if it is closer to 1, the performance would be better. So as you see, as we go from left to right, as we add more variables into our assimilation framework, we see that the multivariate assimilation of ET and soil moisture altogether enhances the performance of our drought monitoring. And this is the same for unbiased root mean square error in the second row, and the last one is the reliability on the left. And as you see, multivariate data assimilation provides a better reliability on the soil moisture, on the drought monitoring, sorry. And on the right, you see the USDM product, open loop, ETDA, and soil moisture data assimilation only, and multivariate data assimilation, and for different drought categories in year 2018, month of February and March. And next slide, please. And here is the, again, drought monitoring in the ACF, the propagation of drought over ACF region during the period of Hurricane Michael. Our developed integrated drought index could capture drought termination on October 9, as you see on the second column on right, October 9, when the Hurricane Michael with heavy rainfall hit the ACF region. However, the USDM failed to detect the tropical storm footprint on ACF region and detected the drought termination on October 16 with 1 week delay. So that was another actually advantage of this framework that can detect drought in real time. Next slide, please. And further enhancement of our drought monitoring that is underway right now is that here we are using both MODIS ET that we used before and SMAP satellite soil moisture instead of the SMOPS. SMOPS was the NOAA product combination of different satellites, as I mentioned before, but the SMAP is the NASA product. So the developers of SMOPS from NOAA did a very rigorous comparison between SMAP and SMOP, and they concluded that SMAP is more accurate than the product they generated. So that was the reason that we went after the SMAP product. In fact, I'm going to show in the next slide our downscale product that is already available on my website. But before that, I'd like to mention that we replaced the weak hydrologic model with NOAA MP land surface model to better characterize the hydrologic fluxes. And the model basically accounts for the vegetation canopy energy balance, layered the snowpack. Of course, snowpack is not a concern in the southeast, but we are doing over the continental US. The frozen soil and infiltration and soil moisture groundwater interaction and related runoff production and vegetation phenology. These are all seen in NOAA MP land surface model, which we find it better. And again, we use the MODIS evapotranspiration in our framework. Next slide, please. Here is the downscale satellite soil moisture product at 1 kilometer spatial resolution over across the continental US. We published this paper in 2019. We use a machine learning approach for that, and we use variety of data sets like the MODIS NDVI, and also land surface temperature data at 1 kilometer resolution, and precipitation at 4 kilometer resolution, topography data, and SMAP soil moisture at native resolution of 36 kilometers. We combine them and put them into the machine learning framework, and we downscale the product at 1 kilometer resolution. That we tested this downscale product rigorously using 300 sparse soil moisture network dataset using US and Climate Reference Network, USCRN, and also Soil Climate Analysis Network SCAN. And Rachel, if you just click on that website, I can show where that dataset is available. And as you see here, we made this product available on the website. The product is downscaled every day from 2015 when the soil moisture active passive microwave data became available till today. And if there is any request on this data, if you go further down, scroll it down, Rachel, please, you see that the request can be made here for any period of data or any region at the continental US. Anyone is interested, you can send this request and we will provide the data set quickly to you. And if you scroll up, and finally, we put all this product, you go to the next tab, USDM and Integrated Drought Index, yes. And this is the product, actually, we made it available just a couple of days ago on the website. We are still working on it. On the right, you see the USDM drought monitoring system at weekly scale, and on the left is our integrated drought assessment system using data assimilation, multivariate approach, evapotranspiration, and soil moisture here at 12.5 kilometer resolution. So this is provided on a weekly basis, but we are working on enhancing this and to hopefully make it publicly available. This is a rigorous procedure. It's computationally demanding, so we have to run the data assimilation every week. I guess more resources are needed to be able to maintain this product. But the accuracy of this has been pretty good so far, as we tested on several regions and different years, but we would like to further test it out and make sure that this is providing the right information for everyone, especially for the Southeast. Thank you, and that was my presentation. If there is any question, I'll be more than happy to answer.
Thank you, Hamid. And before we get into questions, Meredith Muth of NIDIS had a big announcement for everyone, so I'll turn it over to her for a moment.
Thank you. I know we're over time, and many thanks to everybody who stuck around. Just encouraging you to check out the new US Drought Portal, which is at drought.gov. We are going to have someone do a little walkthrough on topics that might be relevant in particular to the ACF and the participants in the ACF in next month's webinar. But what I really encourage you to do is to check it out and look at the county and the local level, and you'll see a whole bunch of different products and tools. And of course, we always are welcome to additional feedback and input as we move this forward. This will also complement the ACF drought dashboard that we are currently working on with many of you that are on this call. And I'll leave it at that. Thank you.
Thanks, Meredith. Yeah, we are a little bit over time. I want to thank our speakers, and I do have one question in the chat for Dr. Moradkhani from Steve Burian, who I don't believe is still on the line, but he had asked if there was a drought frequency product that indicates the current conditions in terms of historical conditions.
There is not, but this is not a sophisticated thing to create. We are able to create that frequency map product as well, especially that we have that statistical approach available using a couple of functions, so we can provide that probabilistic information and frequency information on drought.
Okay. If there are any other questions, please put them in the chat box. And in the meantime, I want to thank our speakers, David Zierden, Tom Littlepage, Paul Ancorn, Troy Ephraim, Jeff Dober, and Dr. Hamid Moradkhani for this special presentation today. Please mark your calendars for our next webinar next month on Tuesday, February 23rd, same time, 1 p.m. Eastern, 12 p.m. Central. There will be a video recording posted to YouTube of this webinar, as well as a follow-up email within 48 hours. If you have any questions or comments, feel free to contact me. And thank you everyone for attending today. Have a great Tuesday.